Good morning, students. Welcome to the class on spectroscopy. We were discussing proton NMR spectroscopy. Today we will discuss about integration of peaks and the magnetic anisotropic effect. To discuss the integration of peaks or integrals, I'll just take one spectra for example and I will discuss it. This is benzyl acetate. Of course, we know how to predict the chemical shift values of these protons. This is benzylic proton, as well as this carbon is attached to oxygen. So first aromatic protons are there. We have 5 aromatic protons, so they will give large delta value. So it is given as A, and next one is this one. It is benzylic as well as attached to oxygen, so this will give the next highest delta value. And this is like a carbon, protons and a carbon which are attached to carbonyl carbon, so it is C. Generally this gives a peak from 7 to 8 ppm, and this gives a peak around 4. Since it is both benzylic as well as attached to oxygen, it may increase to 0.5 or something like that. Of course, allylic, we have seen that it will be between 2 to 3 ppm. Now, in the proton NMR spectrum, we used to have intensity on y-axis and delta value on x-axis, right? So in this spectrum, we do expect 1, 2, 3 peaks. So this peak will be for around 5 protons, highest delta value. The next peak, I'll give these values 0, 1, 2, 3, 4, 5, 6, 7, 8. So it will be like this. The next highest peak, next peak will be this CH2 peak. Next peak will be this CH3 peak. And of course, we know we will get a peak at a 0 value TMS. Generally, when we do spectra, when we operate the instrument, we get only these bare peaks. Then what we will do, we will give a 0 to the right side peak. So the last peak on the right side, we will generally give 0. Okay, then accordingly, the scale will appear from here onwards. Okay, so when we process our compound for a NMR spectroscopy, what we will do, we will take the compound and TMS, they will be dissolved in a NMR solvent. So TMS peak will appear, instrument will give only the bare peak. Then what we will do, we will assign 0 to the right side end peak. Then accordingly, all other peaks will be given automatically, will get delta values. Right. Now, when we want to look at the integration of peaks, what is this integration? Integration is nothing but area under each peak. Area under each peak. So when we are doing integration means we are calculating the area under each peak. Then when we calculate the area under each peak, what information we can get? When we take the ratio of peaks, for example these two peaks, when we take the ratio, then we will get the relative number of protons present in a peak. So what we will get, we will, from this ratio data, the relative number of protons in each peak. each peak. Okay, so that means, for example, this is for 5 protons, this is for 3 protons, right? So when we take the ratio, it will appear 5 by 3, 5 is to 3. We are calculating area here, we are calculating area here. When we take the ratio, it gives like 5 is to 3. It may not be exactly 5 is to 3, one or two points. Okay, sometimes it may be 4.9 is to 3.2 or 2.9, something like that. So when we measure the area and take the ratio, what we will get? We will get the relative number of hydrogens in each peak. So during the processing, what we will do, if you know any one peak, say for example, yeah, this peak we know CH3, it should have 3 protons. Then what we will do? We will give 3 to this area. So instrument is having a program which will do integration. So during integration, what it will do? It will calculate the area under each peak. Then if you know any one peak, then what we will do? Yeah, we know this peak, for example. This peak is for methyl group. It should have 3 protons. Then what I will do? I will give 3 to the area under this peak. When I give 3 to this, automatically, sorry for this, automatically it should be 2 protons, right? Automatically, uh, the area under the other peaks, it will be adjusted according to the number of peaks. So we are giving 0 to the TMS peak. Similarly, we will give a value to known peak. Okay, if you know any one peak, at least one peak, that is enough. So for example, I know this methyl pre, so it should contain 3 protons. So I will give 3 to the area under this peak. Then accordingly, all other peaks will be adjusted and the relative number of peaks will be given. So we cannot measure the exact number, but we can measure the relative numbers using integration method. So when we do integration, we get a graph like this. You know, it will be a continuous line, but we will cut it. We will select the area. So from this point to this point, so that it will measure the area only from this point to this point. So something like this. When we do integration, it gives a straight line, but we need to measure only area between this point and this point, right? This is the only area. So we will select from this point to this point. So it will measure the area here. Then again, we will select a point from here to here. Okay, so like this. So this is the integral. This is the integral symbol. So whenever we take an NMR, we do observe this integral symbol. It measures the relative number of peaks in each peak. So accordingly, we can easily identify the total number of protons in the molecule. Now we will discuss about magnetic anisotropy. Isotropy means uniform, same in all directions. Anisotropy means non-uniform, that is different in different directions. Of course, we know the chemical shift is influenced by electronegativity, hybridization, and magnetic anisotropy. Of course, we know the concepts hybridization and electronegativity. Electronegative atoms will withdraw electrons, so they will decrease the electron density around the proton, so they will have less more resultant energy. So uh, they will be observed at a large delta value. We know these two concepts, but what is magnetic anisotropy and how it influences the delta value? For example, you take benzene. We said its delta value is from between 7 to 8 ppm. Why it is giving such a large delta value? So this is explained based on anisotropic effect. What is anisotropic effect? Yeah, when we have benzene molecule, it has 6 pi electrons. So these pi electrons are occupied above and below the plane. That means these 6 pi electrons will be placed above the benzene ring and below the benzene ring. Right. When we place the benzene molecule in a magnetic field, what will happen? These pi electrons will undergo circulation. So because of this circulation, they will generate electric field. So that is what is called local current or local electric field. When we say there is existence of electric field, we also say there is existence of magnetic field. So this is called local diamagnetic field, or in this case we can say local diamagnetic ring field. Local electrical field or local diamagnetic, we also say the electric field, local diamagnetic ring current, local diamagnetic ring current, because it is from benzene ring. Okay, local diamagnetic ring current. So the magnetic field is called local diamagnetic field. Now what it will do? As we know, local diamagnetic field will screen the will protect the protons from the applied magnetic field. As a result, B applied minus B local, right? As a result, it will because of large local diamagnetic field, resultant will be very less. Resultant will be very less, right? Right. But in this case, what will happen? Because these pi electrons are above and below the plane, the magnetic field generated will also exist above and below the plane. The magnetic field will also exist above and below the plane. The magnetic field will also exist above and below the plane. So this is induced magnetic field. This is induced magnetic field, and these are circulating electrons. Right. So when there is a magnetic field, what we say, it is called shielding. It is called shielding. So the local magnetic field shield the protons present in this area from the applied magnetic field, so that the resultant will decrease. Right. Right. So I'll draw one more diagram. Say for example, if I apply a B naught like this, it will look like. So this magnetic field will be aligned opposite to this. Right. I'll draw one more diagram. When we have benzene molecule, what we are saying, we are generating local diamagnetic field above and below the plane. We are generating local diamagnetic field above and below the plane. So this is called shielded region. This is called shielded region. If the protons are present there, they will be shielded from the applied magnetic field. As a result, what will happen? The resultant magnetic field felt by the protons in this area is very, very less. So the delta will be very low delta, right? Right. But where are the protons on benzene ring? The benzene ring protons are on the periphery of the ring. They are in the plane and they are periphery of the ring. So these protons are not in the shielded region. Remember, these protons are in the de-shielded region. So shielded region, I am using positive sign. De-shielded region, I am using negative sign. So other than shielded region, it is called de-shielded region. Other than shielded region, it is called de-shielded region. De-shielded region protons will observe very high delta value. De-shielded protons will be observed at very high delta values. So because of that, benzene protons are generally observed at a very high delta value. So for benzene, protons on benzene, they are in de-shielded region, so they have large delta value. Magnetic anisotropy, and one more contributing factor here, it is hybridization. Benzene carbons are sp2 hybridized carbon. They are more electronegative. That means the protons on sp2 hybridized carbon will appear at a large delta value. So due to the magnetic anisotropy and hybridization, the benzene protons will generally appear at a very large delta value in the proton NMR spectrum. Now we can extend this concept to other molecules. For example, take ethylene molecule, a double bond. So in a similar fashion, ethylene molecule is having a pi bond. So that means its pi electrons will be circulating above the plane and below the plane. That means it has a shielding region above the plane and below the plane, but the protons are not in the shielded region, they are in the de-shielded region. So generally they will we will observe these protons on double bond also at large delta values. So for ethylene, the delta value for protons, the delta value for protons is generally between 4.5 to 6.5 ppm. Here it is the only right. Next example is acetylene. Acetylene. We do expect that uh, ethylene is only sp2 hybridized carbon, whereas acetylene is sp3 hybridized carbon. So because of increase in hybridization, we do expect that the protons on sp hybridized carbon should appear at a very large delta compared to ethylene, right? So because of hybridization, we expect a large delta, right? Right, but it is not true. It is an exceptional case. Why? In acetylene, it has two pi bonds. Acetylene has two pi bonds. Say for example, this is the axis. One pi bond will be in this direction, perpendicular to this molecule in the plane. Another pi bond will be in this direction, that means z direction. For example, this is x, this is y, this is z direction. So that means the two pi bonds are, one is along this direction, one is along this direction. That means the pi electrons in an acetylene molecule are surrounded between this, right? They're in this direction and in this direction. That means the pi electrons are surrounding this molecule like a cylinder, like a cylinder. So we can take that the pi electrons distribute around this acetylene molecule. The pi electrons distribute around this acetylene molecule. So as a result, what will happen in the case of an acetylene molecule? This is a shielded region. Why? Why? Because the pi electrons are distributed like this, so it comes under shielded region. So unlike in the examples of benzene and ethylene, where the protons are in de-shielded region, but in this case the estellinic protons are exactly in the shielded region. So because they are in the shielded region, they will have low delta value. They will have low delta value. Generally, we observe estellinic protons from 2 to 3 ppm, between 2 to 3 ppm. Look at the example of aldehyde. Aldehyde protons are generally observed between a delta value of 9 to 10 ppm. Why they are appearing at such a large delta value? Right. One reason is the carbon is sp2 hybridized. Carbon is sp2 hybridized. Second one is the carbon is bonded to more electronegative oxygen. More electronegative oxygen. So because of these two reasons, the delta value will increase, but not to this amount. This is mainly due to the anisotropic effect. Anisotropic effect. So when we have a double bond, above the plane and below the plane will be shielded region and all other will be de-shielded region. So that means the aldehyde proton is in a de-shielded region. Because it is in a de-shielded region, it will appear at a larger delta value. So because of these three reasons, diamagnetic anisotropy, presence of more electronegative atom and the sp2 hybridization of this carbon, generally aldehyde protons will appear at a very large delta value. Now we will take this example. In the case of acetophenone, generally what we observe, the aromatic 5 protons should appear at the same delta value. But in the case of acetophenone, the ortho protons are having large delta value. It is 7.85 ppm, whereas other protons, that means protons at meta or para, they appear at a low delta value. What could be the reason for this? Yeah, the reason is that because of the presence of a carbonyl group on the aromatic system, we do observe shielding and de-shielding, magnetic anisotropy. So when we do that, what will happen? These protons will be in a de-shielded region. These protons will be in a de-shielded region. So because they are in de-shielded region, they will appear at a large delta value. Whereas these protons, they are not related to shielding or de-shielding. So they generally appear at around 7 to 8. Okay, so these two, ortho and meta, they should appear with same delta value, but because the other protons are present in a de-shielded region, they appear at larger delta value compared to the meta protons. Similarly, uh, I'll give you one more example. This is cyclophane. Cyclophane. When we look at this molecule, see this methane group, it is exactly above the benzene ring. So that means it is exactly in the de-shielded region. Sorry, it is exactly in the shielded region. This benzylic protons, they will generally appear between 2 to 3. And next one, of course, it may be 1 to 2. But this one particularly, it will appear at -1. Why? Why? Because it is exactly in the shielded region. When we say it is in the shielded region, it appears at a low delta value, right? This is generally a benzylic proton, so it will appear between 2 to 3 ppm. Then this carbon, which is attached to an sp3 hybridized carbon, so it will appear around 1 to 2 ppm, general alkenes. In analogy, we also expect these protons to appear between 1 to 2 ppm or 0.5 ppm. But in fact, in reality, it is giving a -1 ppm. The reason is that these protons are present exactly in the shielded region.